talking to you about immunotherapy, specifically looking at adoptive cellular therapy in acute lymphoblastic leukemia. So first of all, what is acute lymphoblastic leukemia, or ALL for short? So basically ALL is a cancer that targets the white blood cells. So in a normal child, the stem cells from the bone marrow will develop into either myelin cells or lymphoid cells. So those myelin cells are going to mature to become red blood cells and platelets, while the lymphoid cells are going to mature to become white blood cells, so B cells and T cells. In a child with ALL, those lymphoid cells don't mature; they become like abnormal. So and they rapidly grow, and they become they take over like the bone marrow. So they don't give enough room for the healthy lymphoid cells to grow. It is the most common cancer among children, affecting 3,100 children per year, and 85% of all patients have B-type ALL. So that means that this abnormality occurs in the B cells. There are several causes of ALL, one being radiation exposure, inherited syndromes like Down syndrome, and low immunity to begin with. But an interesting cause I found was something called the Philadelphia chromosome in the genome. So basically, the Philadelphia chromosome is like a cross between chromosome 9 and chromosome 22. So this gene, called the ABL gene in the chromosome 9, is going to break off and combine with the BCR gene found on the chromosome 22. So the resulting BCR ABL gene is the Philadelphia chromosome. And it's found in most of the children who do have ALL. So in this photo right here, this is a blood smear taken from a child with ALL. As you can see, these purple circles are the leukemia cells, so those abnormal B cells are circled. And in this picture, this dark purple area is all of those, the abnormal B cells. So as you can see, as I was talking about earlier, they like invade the entire bone marrow, so they don't leave enough room for those healthy B cells to grow. So a typical treatment for ALL is chemotherapy, and basically chemotherapy is administering a specific combination of drugs to the patient. As Sarah said earlier, chemotherapy is problematic. You can have a lot of symptoms after chemotherapy just because a lot of the other healthy cells, healthy red blood cells, and healthy white blood cells are also targeted with the leukemia cells. So it occurs in 3 phases: the induction phase, which is the administration of the combination of drugs; the intensification phase, which is a further dosage of the chemotherapy drug just to ensure there's no more leukemia cells in the bloodstream or the bone marrow. And typically after this step, if remission does occur, so if no more leukemia cells are found in the bloodstream or the bone marrow, a stem cell transplant is recommended. And then after that, the maintenance phase is done just to ensure immunity is at its highest, so no more diseases or infections can occur after. So 40 to 50% of people show relapse after chemotherapy. So initially when chemotherapy is given, around like a high number of people, around 80-90% of patients do show remission, but 50% of them show relapse. So basically like only 50% of people are actually showing remission after, which if you think about it, after all of the chemotherapy, which lasts about 2 years, is not really worth it anymore, and with all the symptoms, in my opinion. So now, immunotherapy. So immunotherapy is basically, instead of administering a drug to the patient, you're using their own immune system to treat them. So I'm looking at adoptive cellular therapy, which is using the patient's T cells, modifying them, putting them back into the patient, and then allowing those modified T cells to destroy the cancer. So the modified T cells are going to target an antigen that is going to be found on the tumor. the antigen that is targeted by most CAR T cells in all is the CD19 antigen that is found on most B cells, the abnormal B cells in all. And 85%, I mentioned earlier, 85% of children do have B-type all, so it makes sense why these CAR T cells would be modified to target that antigen. So this right here, this blue circle represents the CAR T engineered cell. This orange part right here, these are the domains that I will further explain over there. But this blue part right here, this is the receptor that is genetically engineered on the T cell. So it's going to target the antigen right here represented in the green, and in this case it's going to be that CD19 antigen I was talking about. So once it binds onto the antigen here, it's going to send a signal down to the T cell. So these are called domains, which are synthetic engineered antibodies. So there's going to be a receptor, a domain on top of the T cell, so an extracellular domain, and then an intracellular domain inside the T cell. So once that the receptor binds onto the antigen, it's going to send a signal down into the T cell through those domains to release toxins to kill the cancer and a cytokine, yeah. And it's important, cytokine is important, and I will further discuss that later. So this is basically the process of CAR T cell therapy. So the first step is to take a blood sample from the patient and then separate and isolate those T cells. Then using a disarmed virus, HIV was used for a study that I'm going to talk about later. It's important to know that HIV was disarmed. So HIV did not cure the cancer. HIV was just used to promote the receptors on the CAR T cell. I saw an article saying, oh, HIV cured cancer, but no, it was disarmed. So yeah, the disarmed virus will be used to modify those receptors onto the CAR T cell, and then after they're going to be multiplied and expanded still in the lab. And then usually after they've been expanded, a small dose of chemotherapy is going to be given to the patient just to eliminate prior T cells and any abnormal T cells and B cells, just to make the chances of the CAR T cells work the best. So after the chemotherapy, they will be injected into the patient, and then they will attack the cancer cells. So after around like 2014, Stephen Group and his associates at the University of Philadelphia, they did a study, 3 studies that led to the FDA approval of Chimera, which is like huge. So Chimera was FDA approved in 2017 for children with relapse and refractory B-type all. So relapse just means the cancer came back, and refractory just means other treatments such as chemotherapy and radiation did not work for the patient. So 3 tests were done, 2 supportive trials and 1 pivotal trial that I will be talking about. So in the first supportive trial, 30 patients were given Chimera and monitored over a process of 28 days. So 27 out of the 30 patients showed complete remission after those 28 days, and then 67 showed remission after 6 months, which is pretty good. So the second supportive trial is still ongoing. So data is still being collected for the second trial, and it's estimated to end around like 2024. So lastly, the pivotal study, which resulted in the FDA approval, had 68 patients that were given this drug. The CAR T therapy. 83% showed remission after 3 months, and 75% showed remission after 6 months. So if you think about it, as I mentioned, chemotherapy does take about 2 years to complete, and then after that you might not even you might not see remission statistics, but in only 6 months, 75% of these patients are showing remission. So in about half the time of chemotherapy, remission statistics are a lot higher. So this is a graph showing the statistics of the 3 trials. So as you can see, the amount of CAR T cells in the patient slowly declined as time went on. So in the future, injections of CAR Ts will have to be continually given if you want to see continuous remission. But as you can see, like, it does last a while. So I would say about like a year or 2 years, injections would have to be given again. So lastly, talking about cytokine release syndrome, this has been like the most fatal side effect of the CAR T therapy. So about 19 to 43% of patients that are given the CAR T therapy will show symptoms of CRS. So as I mentioned previously, so cytokine will be released when the T cell releases the toxins to kill the cancer cell. This is because it increases the T cell's function. So once cytokine is released, it will release a systematic inflammation, which will cause more T cells to come and help the modified T cells kill the cancer cell. So the problem arises when like too much of this cytokine is released, also called the cytokine storm. So too much of it can first result in flu-like symptoms like fever, and then escalate dramatically into states of delirium and impairment. But luckily, the FDA has already approved a drug to treat CRS. So a study was done testing this drug, and about 68% of the patients showed remission of CRS. I forgot to mention previously, but chimera has been approved for children 2 years and older. I think the max is 25 years with relapse or refractory all. Yeah.
So how does this subject relate to the main themes of the course? How does it relate to, exponential change?
I think, as I mentioned earlier, this technology has already been FDA approved from the time it's been experimented, which only took about 3 years. So in that way, this technology is increasing. A lot of clinicians like Stefan Group and Dr. Rosenberg, who's also looking into this technology, has also stated how quickly this technology is growing, and it will eventually, in my opinion, overtake treatments like chemotherapy and radiation, just because the remission rates aren't as high with those traditional treatments. Yeah.
Questions?
So you think that this technology is going to overtake traditional methods, but in this course you talked about a bunch of different technologies, and they all seem to be increasing pretty exponentially, and they all seem to be leading towards, treating disease like stem cells, gene editing, and your technology here. So why do you think what you've discussed here is more pertinent than, say, transplantation or artificial generation of bone marrow to insert into specific patients or something?
I think because this technology actually uses the patient's own immune system. You're actually taking their own T cells and modifying them. I think in that way it's going to be more beneficial instead of implanting something and hoping that it will adhere to the patient rather. It's their own body.
Okay. Okay, go ahead.
Could you go back to the slide where you showed the T cell binding to the B cell?
So?
Yeah. So I have a couple questions. First question is how is it that the T cell knows not to attack the healthy B cells, and where's the specificity there?
So that's actually kind of a problem that I was see a lot. So because it's only modified to locate that CD19 gene, right? So healthy B cells also have that CD19 gene. So they're looking at how to better specify like a tumor CD19 gene versus a healthy CD19 gene.
So then how is it used in vivo?
Pardon?
How is it used and how is it actually applied if there's no like actual regulation on that?
Well, it's still going to kill like the tumors with the CD19 gene. So
Okay.
yeah.
Is CRS like a short-term thing, or is it long-term if that drug was given?
If it's not controlled, it could be fatal, like it could lead to death. But because of the FDA-approved drug, it can be controlled around like a week or two.
So
But
flu-like symptoms wouldn't just be like a few weeks and you're good, it'd be like
Yeah,
you
it would-
potentially die.
yeah,
Okay.
like it's going to keep growing until it's controlled.
Okay, maybe I missed something, but so we're modifying these cells within someone, right? Is that the premise behind this?
Well, you're taking
The cells,
their
modifying
cells
them.
out and
Okay.
then modifying them and then putting them
So we have
back.
like a limited number of, cells that we've modified. So when those cells die, so the individual like need re-injections of these cells. But also adding to what Haresh said, like there's also like a list of autoimmune disorders already where the immune system tends to attack their own body, right? And do you think that these cells could have like not just with just the T cells, like the healthy T cells, do you think they could, lead to damage in other parts of the body potentially? Like have the studies mentioned anything about this that you could find?
I haven't seen
Okay.
anything, but yeah, that is a good point to prove, and I think that's what they're trying to figure out, the specific.
So, other questions? Okay, well, thank you